For the following video, let's try using the Arrhenius equation and our rate laws together. So in this case, we have a second order decay reaction. So some molecules just decaying on its own, but in the second order fashion. We know the activation energy for this reaction. It's 42.75 kilojoules per mole. What we want to know is we want to find at what temp will the initial rate be 0.013 moles per liter per second. Specifically for when we're using 0.75 molar. So when 0.75 molar is our initial concentration. Well, we have some data down below from one run. So we started this material at 0.75. We let it run for 2 minutes. It was down to 0.44. Unfortunately, this wasn't the right temp. When the calculations were done, this student had been wrong. It wasn't 25 degrees Celsius. So using this info, can you find at what temperature our rate should be 0.013 moles per liter per second? Go ahead and pause, problem shoot this for a minute, and come on back. All right, if you're back, well, we got to think for a minute. We got a couple things. I've got my energy of activation. I have some rate info. I have some concentration and temp and time info. There's a couple different things that come up when we think about rate laws. There is that my rate is equal to my K, my material to the second power. This is a second order reaction for the decay of one molecule. So we've got this general idea, which also gives us our integrated rate law if we wanted it. 1 over the material at time minus 1 over the material initial is going to be equal to KT. Well, additionally, we're also working with Arrhenius equation, and well, there is the K is equal to A e to the negative activation energy RT. Unless we're solving for A, generally we're probably going to use the natural log of K2 over K1 is equal to negative activation energy over R, 1 over T2 minus 1 over T1. So given the types of things we were given, these are probably the rate law equations that we're thinking about using. Well, we're specifically asked to find what temp a rate is. Not a rate constant, a rate. Well, for that, the only thing here that solves rate directly would be this. My rate constant times concentration squared. However, that doesn't involve temp. We would need to know the K for that temp. The only thing here that involves temperature and rate is going to be our last equation. So if I want to know temp, if that's our goal, is we're trying to find the temperature a certain rate constant occurs. Well, temp is our goal. So we're going to want to find temp 2, or temp 1, just pick one. We'll know the value for the other. We need to solve the unknown. So we need to find the temp. Well, to find that temp, that means I would need to have a temp 2, a K1, and a K2. We're given the activation energy, so we're good there. And, well, I do have some temp data. So probably temp 1 is related to that info over there. And so arguably I do have temp 1. And it's going to be 298.15 Kelvin. That means somehow I have to get K1 from that data. Well, I have concentration initial, I have concentration final, and I have some time. And I know it's second order. So yeah, I can solve K1 from this. That reaction data actually lets me solve K1. So yeah, we can get K1. That means we're just missing K2. How do we get K at the other temperature, the one we're trying to solve? Well, remember that our only equation that directly involves rate doesn't mention temp. It is dependent on the temp, but that's accounted for in the K value. So if I know what my initial concentrations are supposed to be, 0.75, and I know what the rate at that temp is going to be, I can solve the K for that temp. Now, it doesn't tell us what the temperature is at the moment, but it does mean that at whatever temp you get that rate of 0.013 for starting concentration of 0.75, we can solve that K, which means we can get K2. We do have the info here to solve all of these. Well, let's go for the ones that we don't have directly written. Energy of activation was given to us. It just mentioned up above. Temp 1 was given to us. It's 25 degrees Celsius. So let's solve, first off, K1. Well, to do that, I'm going to use my integrated rate law. So 1 over 0.44, concentration at time, minus 1 over 0.75, concentration initial, must equal KT. We know the time was 120 seconds, so 120 seconds. Solve for that K, which we're just going to call K1 because it's from our data for 25 Celsius. So that'll be run 1. Well, 1 divided by 0.44 minus 1 divided by 0.75 divided by 120. We'll solve 0.00783 liters per mole per second. So we can get K1. And so we can go back and say, hey, I got K1. Now I need K2. Well, K2 we said we could find from the rate info. We know the rate at the temp we're looking for. That was given to us in the problem. So 0.013 moles per liter per second must equal K2 times that initial concentration. So we have our initial rate. Our initial concentration was 0.75 squared. We can solve K2. What we'll find is that's 0.0231 liters per mole per second. And so we've got K2. We can plug these in to solve for T2. Natural log 0.0231 divided by 0.00783 must equal negative 42,750 joules per mole, which was our activation energy in the problem, divided by 8.314 joules per mole Kelvin, 1 over temp 2 minus 1 over 298.15 Kelvin. Well, we can multiply the R value over. We can divide the energy of activation down. After we do that natural log, you'll get negative 0.00021 is going to equal 1 over temp 2 minus 1 divided by 298.15, or 0.003354. I can then add that to both sides. What we'll find is 0.003144 must equal 1 over temp 2. Rearrange. Temp 2 is 1 divided by that, or 318.1 Kelvin. We wanted a particular rate. Sometimes this is the case when you're in an industrial reaction. You want to make something a certain speed so that you'll have just the right amount ready in the right amount of time to add to a later step of a reaction. And so you're trying to devise your machine so that it runs this reaction at a certain rate, so that what you create will be produced at just the right speed to match something else. And so what temperature do you need to run this at in order to obtain that rate? And what we find is that it's 318 Kelvin. And so with just the energy of activation and a target rate and a single run at a different temperature, knowing that this was second order, we are able to solve out the other K values and the other temperatures. All these rate laws and rate equations can interact with each other. We just have to know what it is we're looking for and which of these equations is going to be useful for obtaining that piece of info.